Good morning, fellas, and welcome. My name's Ted Howard and I work for Queensland Power in Mackay. We're a total electrical business up there and we do overhauls and repairs for all of the mining industry, including metalliferous mines from here to the Northern Territory. We also service the ports. We've been asked by the coal mining companies and also by the Mines Department to carry out some sort of cable awareness course at all the mines due to the amount of incidences that we've been having of late. Each year we get a card from the Department of Mines listing all the incidents that have happened. These are the ones that have been reported in the coal mining industry in the central region only. This is the one we've got here. This one I'm holding in my hand goes from October 98 to February 99, 4 months. And there's 40 incidences listed in there of cable flashes underground. Now, cable flash underground is the most devastating thing that we can have, particularly if everything's in the right constituents down there, that we will have a flash, we will have an explosion. If we have an explosion, we're going to have loss of life and probably a closure of the mine. We all know what happened to Mara, and we found that this happens usually on about a 7-year cycle. Mara was in 94, so the clock is ticking, fellas. Mines Department's very concerned about it. They're going to come down hard and heavy, and they're starting to now, as a registered mine electrician, to be able to tell you on any reportable incident that might have been caused by the fact that some person didn't follow procedures on the mine site. I think it's important, to talk about these things, that we have a look to see how cables are constructed. 3 of the cables that you're using underground is the only 3 we're going to talk about today. There's a lot more than that you are using, but 3 of them that you are using in particular are these that we have here that we're going to show you. This one here is called a Type 241. Every cable, when it's manufactured, is manufactured to a type number, and that tells you how the actual cable is constructed, the whole of the cable is constructed. So an electrician or a cable joiner can look at the end of a cable and see how it's constructed. He can go to his manual and he will be able to tell immediately what type of cable it is. This one here that we're looking at the present moment is a 241. The 0.1 up there, by the way, means it's 1,000 volts, and the 0.3 means 3,300 volts. We won't worry about that. This Type 241 is a trailing cable. It's used on your miner, it's used on your longwall. It's a general purpose cable throughout the mine. You cannot use it as a reeling cable. You cannot reel this, otherwise you'll smash up all of the conductors inside and severely damage the cable. This particular cable here has a hard outer sheath, and the reason that we have a hard outer sheath around it is to provide mechanical support and protection for everything that's inside, all of these conductors that are hanging inside here. That's what it's there for. We're not allowed to have any cuts or holes through that sheath for any reason. If we do we have to test it in town to make sure there's none there and repair it, because otherwise contaminants get in, and once you get water and moisture and contaminants get in there, then you're going to start damaging all this material inside here, create long-term damage to the cable. We have cables that come into town and we have water in them, and I'll explain that to you later on. So we have this hard outer sheath protecting all this. Now, around all of these conductors inside here is a black material that we call a semiconductive rubber, and it acts like an earth screen around all of those cables, all of those conductors inside. So once we get inside, we find we've got 3 big heavy conductors here. They're colour-coded red, white and blue, and that's only for our advantage, not for anybody else's. Colour-coded red, white and blue. And that's the insulation that's around these live conductors, these big heavy conductors in the centre. They are the ones that carry the power supply to your machine. In this case, a 1,000 volt cable, so we've got 3-phase 1,000 volts running through this red, white and blue material here. Now, this insulation that's around these live conductors is of a specific thickness to contain the 1,000 volts inside. It's a bit like at home, your 240 volt wiring that's running through your house. It's got enough protection on it, enough insulation to prevent the 240 volts from coming out of the cable and creating a fire in your house or electrocuting somebody. Now, if that was a 3,300 volt cable, that insulation would be thicker again. If it was a 6,600 volt cable, it would be thicker again. Got the idea? So the idea is to try and maintain that thickness at all times around those live conductors. Now, on the outside of those, we have these 3 what we call earth wires. Now, those earth wires are required because you're using metal machinery down there, and we're required to have an earth at those machines at all times for your protection and also for the machine's protection. It's a bit like at home. in your home there, you've got, like on your washing machine or on your toaster or your iron, electric iron or whatever, it's got an earth wire on it. The idea of that is if a fault occurs inside the unit, it should go down to ground first and either pop your breaker outside or blow a fuse before it creates any damage to yourself. And that's the reason why we have to have 3 earth wires down there. They're contained in semiconductive rubber as well, or an earth screen as well. Now down the centre we have a very tiny wire here called a pilot wire. Now that pilot wire monitors this earthing system down to the machine and back again to make sure that you have an earth down there at all times. And that's what its main purpose is for, is to monitor that earth wire. It's called an earth continuity wire, or sometimes it's called a pilot wire. It's insulated away from everything else. Now around this insulation on these 3 live phases we have this black material that I've pulled off there, that black material. That is semiconductive rubber as well. That is another protection that's inbuilt within this cable. Go back to when we first started manufacturing cables for the mining industry, they never had a lot of inbuilt protection in them. It was just, for a better word, rubber over the live conductors and rubber around the whole lot of that. Nowadays we have this semiconductive rubber inbuilt there, and we have this pilot wire in there monitoring these earth wires. So cable manufacturers come a long way since the old days, and they are improving them all the time. Now you wonder why this semiconductive rubber is around all of that and around semiconductive rubber that's around all of those. Then it'll go through the semiconductive rubber that's around one of these live phases before it enters the insulation that's around that live phase. Once it goes through that insulation and hits the live phase inside, it's made connection with a grounding medium, and that reports back to the substation. Now we have electronic protective equipment back there that senses that. It's called earth leakage system. It'll trip the power off straight away. So no damage basically is done. No damage is done to the machine or to yourselves. That's one of the main safety features that's inbuilt in the cable. Now the 275 is manufactured identically to the 241 except for a couple of features. In the 275, all of the strands that are in here are very flexible. It's a bit like your extension lead at home, like this fella here. It's very flexible. It's made up of finer stranding and there's more of them. So it's a very, very flexible cable. It's called a reeling cable. It's a type 275. It's used on all your reeling machines, on your shuttle cars, roof boulders, whatever you have to have a reel on, will have a 275 on it. It's made up of fine strands, whereas this fella here is made up of heavier strands and there's less of them for the amount of current that it's taken. So it's a stiffer cable. You cannot use it as a reeling cable. This reeling cable you can use as a trailing cable if you should need to. It's not a problem. Once you get inside this, underneath this sheath, semiconductive rubber is around all of those conductors. The same as this fella here. The only thing that's missing around the red, white and blue phase that you can see there, we haven't got this black semiconductive rubber or earth screening material anymore. It's not there. And people say, well, if it's a safety feature in the cable, why don't we have that? Well, the inspectorate thought it was a good idea, so they approached the manufacturers about it, and the manufacturers came out with a cable called a 280B, which had this material around that insulation. And after it was in use for a very small amount of time, they found that if you put a bit of tension on it and let it off, that the cable used to corkscrew. You guys seen corkscrewing in the end of the cable? That's due to too much tension. These things will corkscrew. You have to put a fair bit of tension on them. So if you ever see any cable that's got a rattling on the end or corkscrewing, that's because they've been stretched or had too much tension on them. Now with the 280B, they found that this thing, that they were corkscrewing a lot quicker than any of these were. And you didn't have to put a lot of tension on them at all. So the owners said, hey, we don't like this, you can take this stuff back. We're not going to use it. So just about all of it went back out of reeling systems. Those that had bought the brand new stuff had taken it out and sent it back, and we came back to the 275 again, and that's how it stands today. So 280Bs can still be used, but as stationary cables, they don't want them in a reeling situation. So they've gone back to the 275 again. Still has the semiconductive rubber around all of it, so if anything did damage the sheath and go through, it'd go through the semiconductive rubber before it went through any live phases and still trip the substation out. So that's the two major differences between those two particular cables that you guys are using on site at the present moment. As I said, there's other types of cables that you are using, but we're only going to look at three here today. The thing that we're trying to eliminate underground is the amount of times that we have a cable flash. We're never ever going to get away from having cable damage. But the problem with us nowadays, we've taken too blasé an approach with these cables. I mean, they've been there forever and a damn day, and we know that we've run over them, we know that we've stretched them, we know that we've flashed them, and it seems to be an accepted practice, but no, it's not on. We have to take more care with these things. What are we doing now if we bust a cable in half underground here? It should be covered up and taped. Now everybody says, why? Why should we do that? I mean, the thing's dead anyway. The reason that we should do it is that, particularly if it's been in an operating situation, these cables heat up due to the current flow through the cable. They get hot. You guys would know that from handling them. If you cut one open like that, as it cools down, it sucks moisture right up the cable. We get cables in town there and we find there's a problem with it, and we test it, and we usually find it's in the plug. So we pull the plug off and water runs out of the plug, out of the back end of the plug. So we clean the end of the conductors so we can do our tests, and we find that the tests don't meet the Australian standard. They're too low. The cable's wet. So we think, well, there's moisture up the cable. The only way we can get it out to any degree is to hang 6 or 7 metres up overnight over our overhead crane rail. We come in the morning, there's a pool of water on the floor. So we know that there's moisture in the cable. So we try to dry out the last 1 or 2 metres in our vulcanisers so that we can get our readings up to refit the plug, which we do. Send it back to the mine. It might be out here for, I don't know, 2 or 3 months before some other damage may occur to it, and it comes back into us. Invariably, when it comes back in, there's moisture back in the plug again. I don't think there'd be one cable anywhere in the whole of the mining industry that's been cut like that, or even cut in half like that, that wouldn't have moisture up it. It's very important that we close that off. As I said earlier, we've got to test for any pinholes or any cuts that are in this cable, and you won't see those. We've got some samples here to show you. You won't see those. We have to do a test on those to find those and close them up. So you can imagine what happens if you've got a hole like that in them, or if it's cut off like that, if it's been chopped in half. It's important that you close it off. Get your electrician to tape it up, or get a plastic bag and wrap around it. As I've said to some of the classes, if the only thing you can do is put rag over it, which is going to get wet fair enough, put rag over it to close it off, that's going to help it. If you can hang it up out of the muck, that's another good idea if you can do it. If you can't, well, you can't. But you should try and do something about it. If you can't do anything else, you should report it. Report it to your deputy or to your section electrician. Once you make sure it's isolated, make sure that you close that up. It's very important that you do it. Okay, we talk about cable squashers. That was one. The next thing that we're concerned with is the fact that you guys are using this nylon rope out here, and we have to use rope for all sorts of things, of course. We're not going to ever do away with it. But one of the things that we want to do away with is the way that it's tied onto cables. Now, we said before how important it was that we maintain the thickness of this insulation that's around these conductors. It's very important that we do that. Once you start squeezing down on the outside of this sheath here, whether it's with a rope, whether you run over it, or whatever, whether you squash it, I can do that with my hand just by squeezing that with my hand. This is a pretty hard sheath and I'm not strong. Just by squeezing that with my hand, I can make the insulation around those live conductors inside there deform. And what happens, when you squeeze down on this stuff, it starts to flatten out on a couple of corners. Once it starts to do that, that means the insulation has got thinner because of that fact. Once it starts to get thinner, then that means it doesn't have the same opposition to the voltage that's inside anymore, and the voltage will blow a hole out through the side of it because it's looking to get some other medium. We had this one came into us with this nylon rope tied around it, and it squashed down into the outer sheath, and the damage happens to be right under there. Now, we haven't cut the rope off because we kept it for a sample, but just the way it's been tied, and it's had a fair bit of force on it, it's squashed down and created some damage inside here. Now, if you're going to have to hang these things, sure the hell we can hang it just in a loop like that. So if it's got somewhere to go. If it gets jammed, it's got somewhere to go. It doesn't have to have a couple of half hitches around it, or granny tie or reef knot wrapped around it. This one here, which I'll pass around, when it first came into us, I thought it was a bit of radiator hose. If you have a close look at it, you can even see the fibres from the rope are still in it. The damage, of course, is under there, and we'd wonder why. The other thing to be careful of, guys, we've got a lot of metal machinery underground. Cables lay on the metal machinery, and the machinery is moving. It'll start rubbing on this hard outer sheath. Once it starts rubbing on it, it'll start rubbing through it at some stage. And once it starts to rub through it, the only thing that you've got underneath there is this insulation that's around these live conductors. So if it rubs through the outer sheath, it'll start rubbing through this insulation on the live conductor. When it starts to thin it down enough, the voltage inside, as I said before, doesn't have the same opposition or resistance to it. It'll flash out to the metal object that's rubbing against it, which is earth, and you'll get a flash in that point. Now, if you happen to be at the face at that stage and you happen to hit a pocket of gas, then you could be in deep shit. Okay? So very careful that observe where these things are on machines. If they look like they're starting to rub through, if you can safely remove them yourself, relocate them, do so. If you can't, report it. At the end of the day, if the only thing you can do is report it, report it. This one here has rubbed all the way through the sheath. Completely, all the way through. I don't have the other section, but it rubbed through the other section as well. There was a flash on it because the conductors were damaged. So it's important that we maintain the thickness of the insulation that's around those. All you need to do is say, hey, I think somebody's run over the cable, but mark where you saw the guy run over it. It's very important. And the reason that it's important is that when it comes into us, if the mine decides to change it out, if it's been reported, if we can't find a fault on it, we'd send the damn thing back out. But if it's marked where it's supposedly got run over, then we can open the sheath up and we can have a look inside to see if any of this is damaged. And I can bet you anything you like, if it's been run over by a machine, you'll find some damage. And what happens is, when that squashes down, it cracks the insulation open. Okay? When it goes off it, the insulation will close back up again, but the crack's still there. Now, quite often, with all our sophisticated test equipment we've got and we get it in town, we can't locate where that is until the profile of the cable is changed. And quite often we've got to roll it on and off a reel to be able to get it to break down where it is. But if it's marked, at least we can open it up there and have a look at what's inside and say, yep, that's okay there, and send it back. I'm not saying that every time you run over it, you're going to crack it. But you can do damage inside, as we said. Once you start to thin that insulation out, you're creating damage straight away. This particular piece of cable here, as I said, I only brought it as a sample to you. There's a cut that goes right through the outside of this cable, and it goes all the way through to the live conductors inside, the copper conductors that you can see on the end here. The cut goes all the way through to those. Now, for us even, to look at it, it looks like a nothing thing. This one here, we're talking about holes in the cable. I've marked this one. You find that there's a hole right through it. We have to test for those, and we have to repair them if we find any. And we'll do a test later on a cable here to show you how we do that. This cable here was on the surface. There was 110 metres of it on a reel, except for the last 20, which was laying on the ground. It had been up there for some time. They decided they wanted to use it for something, took it underground, and after they got it all connected up and everything, they found there was holes in the cable for 20 metre length of it. They sent it in to us to have a look at, and we found that it was white ants that had caused this. They've eaten all the way through the cable. So storage is another important thing up on the surface, that you keep any rubber cables like this off the deck. This cable here, fellas, it's type 241. It was on a machine and it had become damaged at some stage. We don't know when. It could have been there for a long time. But for all intents and purposes, it was facing out that way. So you're looking at it from the front there, that's what you would have seen on the machine. Looks to be nothing wrong with it. However, on the back side of it, the outer sheath had been torn off for half a metre. Had been torn completely off. Now, because no damage had been done to the insulation around the live conductors inside, there was no fault. I mean, you can take all of the sheath off all these conductors if you want it for the full length of it and just hang the conductors there, and as long as that insulation's not damaged, there's not a problem. Okay? So this was torn off. Now, when it got torn off, that black material that we looked at before, that semiconductor rubber that's there, a piece of that got torn off the blue phase inside here. And it mightn't sound very exciting, but a piece of steel if it happened to spear down and go between everything that's in there, that semiconductive rubber, go through the insulation into the live phase, you could have a situation where you would have a live piece of steel sticking out of that cable. Don't forget, you can't see that. It's on the back side of the cable. So at some stage during a shift, there's still no fault occurred at this stage, even though there's a bit of live steel sticking out of the live cable inside there, because it's not touching any of that semiconductive rubber. Some stage during a shift, if you had to relocate that cable and you reached over and grabbed hold of it, you could grab hold of that live piece of steel that's sticking out of it and get electrocuted. Could get killed. Now, a situation occurred at an open cut mine in the area and was on a drag line. I don't know if you've seen a drag line cable, but they're fairly hefty, big things. They're usually about 305 metres long, these things, and they're very big. For those of you who don't know, on the drag lines there's a bucket hangs off the end of it, and it's got 4 ropes on it. There's a couple of hoist ropes and there's a couple of drag ropes. When they're made off, they put new ropes on them, they leave about a half a metre tail hanging out the end of steel rope. Now, it's all very neat, it's twisted in its right lay and everything. After a couple of shifts, that lay splays out all over the place. Big sharp pieces of steel. The boilermaker comes down during maintenance and he cuts it off nice and neat where it goes through the clamp, and it looks good. But all of the pieces fall in the bull dust and they never pick them up, they leave them there. The dragline comes along dragging its tail behind it, and a piece of the steel spears down through the outside of this hard sheath. Now, on the dragline cables in those days when this occurred, the material inside here, we looked at semiconductive rubber or earth screening. On these cables it was made of coppered conductors, and they were just wrapped around this insulation, just wrapped around it. Okay? Now, what had happened, due to the fact that the machine had been working this cable over some time, the actual strands parted inside, and this bit of steel actually in fact had gone down between the strands and not touched them, gone through the insulation and gone into a live conductor, 6,600 volts. Now, the oiler, who's the dragline operator's offsider, he went down to relocate the cable. He was a cable handler, and they normally bend down and pick it up and put it on their hard toe-cap boots so they can put a rope around it to drag it with the Toyota to relocate it. He bent down and grabbed hold of the cable, and next thing he knew he was laying in the bull dust looking at the sky. The substation tripped out. They got us to go down to investigate. We found that it tripped on earth leakage. We checked the cable out, we tested it and couldn't find anything wrong with it. So we went down to the operator and asked him what happened, and he told us. We went down to where this guy had picked the cable up, and when we had a physical look at the cable, a visual look, we found a short piece of steel sticking out of it, and we said, well, why didn't it trip the substation out? If he got electric shock off it, why didn't it trip the substation out? And that's when we cut this outer sheath all the way around and lifted it up to have a look inside, and we'd found this piece of steel that speared through, gone between the earth screenings into the live conductor. Now, this can happen with our cables underground. While these are, for a better word, 99.9% absolutely safe, there's a lot of times they're not, and there's a lot of times incidents can occur. Now, this piece here, I've put a piece of steel in there so you can observe it, but that piece of rubber, semiconductive rubber, was torn off that blue phase. When you squash these cables or run a vehicle over them or bend them, what happens inside is you start to stress this insulation that's around those live conductors, and once you start to stress it like that, you start to get it flatten out like that. So all of the electrical stress is in that area, and that's where the damage will occur, in that area. And people say, well, what's the bending radius of cables? You know, what should it be? For a reeling cable, such as these ones that you're looking at here, we'll take this one here, say on a shuttle car, we'll take it at 40 mil. The diameter of the cable is 40 millimetres, of the cable itself. The bending radius is 10 times that, so the radius is 400 millimetres. Now, people will say, well, hang on, what about a cable reel on one of these shuttle cars? There's no way in the world that the reel on that has got a radius of 400 millimetres, and that's true. The thing about that is, it's a specified piece of equipment for underground use, and these measurements that we give you are the recommended ones from the manufacturer. Depending on what the situation is, whether you have a cable in a static situation, such as up on the surface on a reel, waiting to go away for repair, or one that's come back from repaired, or one that's in a continuous reeling situation, or one that's going through sheaves, you'll find that the bending radii of those change, and they change for the different voltages. One we'll look at later is the lead almond one, or the Ht1 as you guys like to call it underground. We all feel that that's not being looked after as good as it should, and we'll go into that one later on. And you guys got cattle, this will be a good cattle prod for you. You got kids? Did you say? I can actually touch that on the cable where there's no cuts or holes, and you'll notice that there's no flash at all, but all you have to do is get fairly close to these things. The dangerous thing about this is that you can actually cut the sheath of these cables open, and once you do that, if you happen to have the semiconductive rubber that's around the insulation inside and it splits, it wants to walk away or move away from the insulation that it's protecting. And if you don't report that somebody's run over it, then you could have your mate coming on another shift where we have this outer sheath is open. We have the semiconductive rubber that's moved away from the insulation that's over that live conductor, and we could have a split in this insulation that's inside, and still no fault has occurred, and that can happen. You have somebody come on another shift and they have to move that cable, and once they move that cable, they've changed the profile of it. So if the cable was laying in a certain manner and he picked it up to change it, to move it, he's changed the profile. If that gap opens up and the voltage inside can see another medium to go to, it may flash. It may flash in his face, it may flash in his hand. It may even make contact with his hands. He may get a shock or electrocuted. It's important that you report it. Since we've been running the courses, we've found that most mines, if it's been reported that a cable's been run over, that most mines are changing the cable out and sending it in to get checked to see if there's any damage been done. It's important that you mark it. If the power hasn't gone off, it's very important that you report it. As I say, if you see a cable that's getting rubbed, or it could be in a dangerous situation, if you can't relocate yourself with safety, your own safety in mind, report it. At the end of the day, if the best you can do is report it, then you should be able to go home with a clear conscience. If somebody got hurt during the night and it happened to be reported that it happened to be in the area which you knew about and nobody else, I think you'd feel pretty bad about it. Very important that we do those things. That's the infernal triangle, fellas, for those that don't know it. Source of ignition, explosive material, and oxygen and air. How that relates to us. So we have our cable flash, or we have our electrical spark, methane and coal dust, and oxygen and air. We're all required to work to an Australian standard. It doesn't matter what we do or what we've got. Everything in this room, the clothes you wear, the lighting, floor material, the walls. We have to have a common base to work from, otherwise we'd have backyard jockeys making every bloody thing. We don't need that. So we have to have a common base to work from. That's why we have to have an Australian standard. It's the minimum standard required to make something. We are required, everything in this mine, including everything underground, is required to work to an Australian standard of some kind. I have one in my hand here, which relates to what we're talking about. It's called Australian Standard HB13. It says, what is a hazardous area? There's a danger of an explosion or fire occurring whenever flammable or combustible materials are handled. This is graphically illustrated by the dreadful toll taken by coal mining explosions in the past. For example, in the last century, hundreds of lives were lost every year. 361 people were killed in one accident alone. In all these situations, electricity is used. To prevent any of the electrical equipment becoming a source of ignition for an explosion, special precautions have to be taken in the design, construction, installation and continued maintenance of such equipment. Now, it's our belief that the manufacturer of these cables builds it specifically to an Australian standard. He's not below it. We believe that we repair the cables and test them to an Australian standard. We don't believe that totally the end user, which is you guys on site here, comply with all the requirements to the Australian standard. I mean, all we're worried about is getting coal out, aren't we, at the end of the day? So it's very important. We had a look at the conditions for an explosion to occur. One of the gases they mention here is methane. Combustible dusts, they mention coal. Well, a UEL is an upper explosive limit and an LEL is a lower explosion limit, and that's set for everything. It doesn't matter what it is, whether it's dust, gas, vapour or whatever. They're all different. So if you've got concentrations of methane between 5 and 15 and everything else is right, you have a flash big enough, you will get that methane to ignite. If it's outside those limits, you won't. It's the same with anything else. That's what UELs and LELs are. Now, at the bottom of this Australian standard, there's a table which relates to this. A match will generate 700 degrees C. If we set our home welder at 100 amps, roughly it puts out about 80 volts. If we multiply the 100 amps by the 80 volts, we get 8,000 watts of energy. That's the amount of energy that's required to melt that 6mm steel plate. The amount of energy required to melt that 6mm steel plate. 8,000 watts. And that's at 1700 degrees C. If you pull a cable in half underground or flash a cable, run over it, squash it, flash it, you've got 10,000 amps at 1,000 volts. So here we've got 10 million watts of energy as against 8,000 watts at 1700 degrees C. What do you think the temperature might be in the area where that cable's flashed? Too hot. About 20,000 degrees C. 20,000 degrees C, which is bloody hot. This table at the bottom here gives us the temperature that methane will flash at. Characteristics of some common flammable liquids, gases and vapours. Methane. Ignition temperature in degrees C, 537. What's our match? 700. That's one of the reasons why you can't. Because the match is hotter than what the level, the UEL, the level at the ignition temperature that methane will go off at. And it says here explosive limits 5 and 15. Because we've got contactors closing in and out and we've got transformers that are supplying equipment that take heat, the box heats up. Now we're only allowed to let that box, the extremities of the box heat up to 150 degrees C. And the reason for that is that coal will start to burn around about that stage. And that's called a layer ignition temperature. Any coal dust that lays on top of anything down there that can heat up. So that's a layer ignition temperature. Cloud ignition temperature is what a dust cloud will go off at in a cloud. So from this Australian standard, the low ignition temperature, previously called the glow temperature, is the lowest temperature at which a heated surface can ignite a layer of dust. A cloud ignition temperature is the lowest temperature at which a dust cloud ignites. An ignition source is a source of energy sufficient to ignite an explosive atmosphere. Sources of ignition caused by electrical means may be divided into two types as follows. An energy source such as electrical arcs or sparks, a hot surface. Again, at the bottom here, there's a table at the bottom of this standard, and it says characteristics of some common combustible dusts. Coal. In a cloud formation, coal will go off at 610 degrees C. Our match is 700. That's another reason why we can't. In a layer, on a surface, 170 degrees. That's why we have the electrical equipment set with a thermostat control so that if it gets to 150, it'll shut the machine down. This paper here, 1966 Dust Summit, was held in New South Wales. They came worldwide to attend this. I'll just read some excerpts from it. Dust explosions are not a new phenomena and are associated with many industries. In the early part of this century, there were several coal mine disasters that kills several hundred people per incident. Clearly the potential for significant loss of life and injury is when a dust explosion exists. Clearly when any flammable dust is handled there's a risk of an explosion. The object is to highlight the role of the ignition and reduce the explosion. Requirements for a dust explosion. For a dust explosion to occur, a combination of circumstances must exist simultaneously. A dust cloud has to form containing particles that are sufficiently combustible to cause an explosion. The dust cloud has to have a concentration between its flammable limits, the UELs and LELs. There has to be sufficient oxygen pre-mixed in the dust cloud, and there has to be an energy source that has a sufficient energy density and total energy to ignite the mixture. Thus, it is possible to reduce the potential for an explosion by preventing these conditions from occurring. It is desirable to minimise the chance of ignition by controlling the known ignition sources. The first step is to identify the sources of ignition and then remove them wherever possible. Electric arcing is the one that's mentioned. Ignition sources are normally characterised by the type of energy they introduce. Electrical is mentioned again. The more energy contained in the spark, the higher the ignition temperature can be to obtain ignition. And we just had a look at the wattage or the energy dispersed by a cable getting flashed in relation to our welder. It's a lot higher. Flames will always ignite an explosible dust cloud, and smoking should be banned and enforced. Now we've had a couple of incidences. We had a miner operator reverse out from the face at the end of his shift, which was very good. He took the cable forward over the picks, parked his machine up, reversed it out, parked his machine up, and away he went. The next crew came down, had to do some sort of maintenance on the machine, and one of the guys started up the heads without checking to see where the cable was and tore it into 20,000 pieces, flashes and arcs and sparks. So then it took them a couple of hours by the time they changed the cable out, got it on, they still had to do the maintenance that they had to do to the machine. So there was a fair bit of production downtime lost. The other thing they do is that they take often take the cable up alongside the tracks, which is okay when they park the machine up. We've had pre-shift crews go down and actually put the jacks down on the cable and bust it. We had one where we had a shuttle car ran onto a cable and they decided to stop it where it was rather than run it off in case they created more damage. The guy said, "Oh, this is no trouble, we can put we'll put some jacks down and jack the thing up." The only trouble was they put the jack on the bloody cable and jacked the machine up and busted the cable. So it's very important that we check these things, and it's good to see a few guys have got some sort of check material that you can use there. Okay? So moving along to what we were talking about there before, when you stretch a cable, there's several things that happen. Rubber being as resilient, we call it rubber. Rubber being resilient as it is what it is, comes back to where I wanted to go before. The trouble is with these copper conductors, you put enough pressure on them, you stretch them, so they get longer and they get thinner. And once they start doing that, they start breaking up inside. Once they start breaking up inside, you don't have the same current rating capacity of the cable anymore. It's not there. So the cable will heat up, and it'll heat up to a stage where it'll be like a fuse and blow, depending on how much load's on it. Very important that we don't stretch them. It's very important on the machines that have reeling cables that they have the correct pressures set at all times. So another thing for maintenance crews to look at. And with the electricians, it's very important that they check the cutout switch that's on the cable reel compartment itself to make sure that that's operating. It's not good enough just to watch it pop up, push it down and watch it pop up. You have to test the circuit to make sure that the switch inside is actually activating, it's operating. For those of you that you don't know, on the cable reel there's a large button on the cable reel itself, so when you put the first layer of cable down, it closes that off, which closes off the pilot circuit and allows you to be able to power the machine up. If you run too much cable off it, it should pop up and stop you before you pull the cable out of the banana plug. So when you stretch these things and they're trying to come back to where they were before, they knuckle like that, apart from starting to split up. They knuckle like that particular one there. And you can imagine what that's trying to do. It's trying to push out through this insulation material that's around it. So once you start to try and push out through that, you're thinning that down and you're creating a problem again. This cable here, there was 350 metres of it, came from a ship loader. The original cable that was on there got damaged. They sent it down to us for repair. In the meantime, they had another cable in the yard that they thought was a reeling cable, and they put it on. We repaired the other one and sent it back to them. After a couple of months, the one that was on there faulted. They sent it to us to have a look at, and it was completely shattered like that all the way through. All those spiky bits that you see there was broken up all the way through the 350 metre length. When we investigated it and had a good close look at it, we found out that it was a trailing cable and not a reeling cable. It wasn't meant to be reeled, and that's why it smashed up. 350 metres had been thrown away. These are done in lays. These strands are done in lays. This outer lay, when we found where the problem was, and we opened up that insulation there, all of the copper conductors that aren't there anymore fell on the ground because they were all broken. And if you have a look, you can see where the tinning that's over the copper has started to wear off on the second lay that's underneath there, and you can actually see the copper itself. 22 seconds it takes. 22 seconds, a long time. 22 seconds with a gas axe to cut through that. When you get one of these cable flashes, because of the amount of energy that's dispersed, the amount of temperature that creates, that vanishes in a flash. It's quicker than you can blink. And it just ionises that and vaporises it into gas. It's gone in an absolute blink of an eye. These are cable flashes, guys. When you see these, if you have a look in one end, you can see the conductors sticking out. If you have a look in the other end, you see nothing. That's because that cable has been damaged, been flashed, and you've had all of that vaporised inside there. This cable here was off a shuttle car. It's got 3 cracks right through the sheath. The sheath's cracked open. If you have a look in the larger one, you'll find that there's no conductor in there at all. It's vanished. External flash. The other 3 conductors, if you look at either end, you can see the conductors coming out the end. We've tested them. The whole 3 of them are open circuited, which means the whole 3 have flashed due to a squash against the rib, most likely. For all intents and purposes, looking at the outside of this cable, there was nothing wrong with it. Not a damn thing. When we tested it and found where the fault was, the whole 3 conductors in there, and that's very heavy duty cable, that, conductors in there, the whole 3 of those conductors are open circuited. And if you have a look at the one that's showing, which is the blue phase, you can see where there's about 20-25 mil of cable not there anymore. Okay guys, the electrical cables in use at this mine transport electricity from one point to another to safely operate machinery. So safe handling methods, locating, relocating, anchoring and tying of all electrical cables in use, and in particular in the underground coal mining industry, is of paramount importance, as damage to cables can provide the potential element in creating a serious and devastating accident. The result can range from electrocution or shock to a serious fire, to an explosion, to significant loss of life. Clearly, when any flammable material such as dust, coal dust or gas, methane and oxygen mixture is present in sufficient concentrations, then the third element, ignition source, is readily available when the ever-present electrical cable is damaged by an external flash when it's created. Electricity can be extremely dangerous if not handled safely